Greetings to one and all. First of all, I wish to thank CAT DLC for giving this opportunity. Next, I want to thank Dr. Vimal Rao, Joint Director of GAT DLC, and Dr. Jaswant Singh, Director of GAT DLC, for their help. I also extend my sincere thanks to Professor A.K. Bakshi, Chairman, Professor K.V. Abhanamurthy, Vice Chairman, for the semi-geeking development project. I extend my sincere thanks to our principal, my colleagues, and also the management of Peerado Arts and Science College for their constant encouragement to carry out this work. Balance bond theory was developed by Linus Pauling in the year of 1928 to understand the concept of hybridization of atomic orbitals in complexes. Uh, Before going into the topic, we have to know what are the prerequisites needed to carry out this work. First of all, we have to know how to calculate the oxidation state of the compounds. This video helps us to understand how to calculate the oxidation state of the complexes. Salient features of VP theory. VP theory describes about the different type of hybridization involved in complexes. It also gives the knowledge about the geometry and the magnetic properties of coordination complexes. Postulates of balancement theory. The central metal atom or ion lacks available number of a vacant orbitals equal to its coordination number. These vacant orbitals form a covalent bonds with a ligand orbital. The ligand have at least one sigma orbital containing a lone pair of electrons. A covalent bond is formed by the overlap of a vacant metal orbital and filled ligand orbitals. This complete overlap leads to the formation of a metal ligand sigma bond. A strong bond is formed only when the metal orbital overlap to the maximum extent. This maximum overlapping is possible only when the metal vacant orbitals undergo a process called hybridization. A hybridized orbital has a better directional characteristic than an unhybridized one. In addition to a sigma bonds, bipons also be formed by the overlapping of filled metal d orbitals with vacant ligand orbitals. The type of hybridization determines the geometry of the molecules. In transition metal atom or ion, either inner n-1 d orbital or outer n d orbital may take part in hybridization. In complex formation, Hooke's rule of maximum multiplicity is strictly followed. The ligand with coordination with to form sp hybridization with a linear geometry. If its coordination number is 3, it forms sp2 hybridization with trigonal planar geometry. If coordination number is 4, it will either form sp3 or dsp2 hybridization with tetrahedral or square planar geometry. If its coordination number is 5, it forms dsp3 or sp3d hybridization with a trigonal bipyramidal or square bipyramidal shape. If its coordination number is 6, it forms sp3d2 or d2 sp3 hybridization with octahedral geometry. Applications of valence bond theory for complexes. Before going to application, we have to remember the such facts. The outer orbital complexes contain a relative more unpaired electron than the inner orbital complexes. The spin-free or high-spin complexes is called outer orbital complexes. Spin-paired or low-spin complexes are called inner orbital complexes. Working with valence bond theory. The following steps are involved in working with valence bond theory. First step is to identify the central metal atom and the ligand. Consider hexamine cobalt 3 complex. Here the central metal atom is cobalt and the ligand is ammonia. Second step is to find out the oxidation state of central metal atom in a complex. Here cobalt has plus 3 oxidation state. Third step is to find out the atomic number of central metal atom in its excited state. The atomic number of cobalt is 24 in its excited state. Fourth step is to ascertain the electronic configuration of central metal atom in its excited state. The electronic configuration of cobalt 3 plus is argon 3d6. Fifth step, fill the electrons in orbitals according to the Kunz rule of maximum multiplicity. Here, 6 electrons are arranged according to the Kunz rule of maximum multiplicity. Sixth step is to identify whether the ligand is weak field or strong field ligand. If it is weak field ligand, spin pairing is impossible. Otherwise, if it is strong, pairing is possible in its excited state. Ammonia is a strong field ligand. Spin pairing is possible. All the 6 electrons are paired and we have 3 b orbital and 1 s orbital and 2 3d orbitals are vacant. Next step is to examine how many ligands in metal complex and each ligand can donate a pair of electrons and form the hybridization. Here 6 ligands, each of them donate one pair of electrons and form D2sp3 hybridization. Next step is to determine the geometry of the complexes according to the hybridization. It formed the D2sp3 hybridization, so this complex will have octahedral geometry. Last step is to identify the magnetic properties of the complexes. If it has unpaired electron in its excited state, it is paramagnetic in nature. The spin swap paired, it is diamagnetic in nature. The complex does not contain any unpaired electron in its excited state, so it is diamagnetic in nature. Here we are going to know about some more examples also. First example is for outer orbital complexes. Which one we are going further in details. Outer orbital complex is one which form the outer d orbital which can take part in the hybridization. Consider the hexamine copper plus complex. Here the central metal atom is copper and the ligand is NH3. The oxidation state of central metal atom in the complex is +1. The atomic number of copper plus is argon 3d10. We fill the electrons according to the Kunz rule of multiplicity in 5 3d orbital and the complex will use outer 4d orbital for hybridization, so it is called outer orbital complexes. Here 6 ligands form the sp3 hybridization and form the octahedral complexes. It does not contain any unpaired electron, so this complex is diamagnetic in nature. Next complex is manganese complex. Here the central metal atom is manganese and the ligand is Cl minus. The oxidation state of central metal atom is +2. The atomic number of manganese is argon 3d5. Here it have 5 unpaired electrons, so this complex may be paramagnetic in nature. It uses s orbital and 4p orbital for hybridization and form sp3 hybridization and exhibit tetrahedral geometry. Other example is copper complex. Here the central metal atom is copper and the ligand is Cl minus. The oxidation state of copper is argon 3d9. Electrons are filled according to Kunz rule. It has one 3d orbital and 4s orbital and two 4b orbitals are vacant. So it forms dsp2 hybridization. So this complex is square planar in nature. Limitations of Ernst-Mohn theory: it fails to explain the color and spectra of complexes. It does not give a satisfactory explanation for the magnetic properties of complexes. It can only predict the number of unpaired electrons in the complexes. It does not account for the relative energy of different geometries. It does not explain why nickel 2 plus, lead 2 plus, and silver 2 plus, etc. with the D8 configuration do not form the excited 5 coordination complexes. It does not clearly explain why this theory prepare only square planar complexes geometry than the trigonal, tetrahedral, and tetrahedral geometry of the complexes. It gives too much importance only to the metal atom, but the importance of ligands is not stressed. It cannot provide the explanation for the fact that certain complexes are level than the others. Place 2 based on nuclear theory, determine the hybridization and magnetic properties of the following complexes. Your answer is here. First complex is cyano iron 4 minus complex. Here the complex have orgon 3d6 configuration. The 6 electrons are arranged according to the Kunz rule of maximum multiplicity, and the ligand 6 ligands donate 2 pair of electrons and form the D2sp3 hybridization. This complex have octahedral geometry. It does not contain any unpaired electron in its excited state, so this complex is diamagnetic in nature. The second complex is iron Fe6 3 minus. Here the complex have argon 3d5 configuration. The 5 electrons are filled in 3d orbitals, so it utilizes 4s orbital, 4b orbital, and 4d orbital to form the sp3d2 hybridization. So this complex have octahedral geometry contain 5 unpaired electrons. So this complex is paramagnetic in nature. Next example is nickel complex. Here this complex have 3d8 configuration. The electrons are filled in ground state according to the Kunz rule. In excited state, the 2 electrons are paired and form the dsp2 hybridization. So this complex has square planar in nature. Here there is no unpaired electron, so this complex is diamagnetic in nature. The last complex is zinc complex. It have orgon 3d10 configuration. So 4s orbital and 4b orbitals are utilized for hybridization to form the tetrahedral complex with sp3 hybridization. Here there is no unpaired electron, so this complex is diamagnetic in nature.